chapter 10. Alright, so 10.1 is again the review preview that you can read. 10.2 is really where this starts. So we're going to look at 10.2 to 10.3. And basically here what we're doing is we're looking at two variables. Two variables that are paired. So we've got two variable paired data. X's and Y's. For example, shoe size versus height. We had that in our data, didn't we? Maybe I forgot to collect that from you. We can't see it now anyway, but that's a good example. So we'll look at an example in your book instead. But we've got pairs of data where we're looking for, is there a linear relationship? Is there what's called a linear correlation? And the way we're going to look at answering that question is first to draw a scatter plot. Actually, we're not going to draw a scatter plot. We're going to have our calculators generate a scatter plot. So I'm going to show you how to have your calculator have your calculator. I have to get that working so I can show you. Or draw scatter plot. And basically what it's going to do is it's going to plot the points, just like in the algebra class. You know, the X's and the Y's, we're going to have these ordered pairs. For example, shoe size versus height. Turns out that there's typically a relationship there. Both of my classes yesterday had a definite linear correlation where the bigger their feet, guess what? The taller they were. So there's some variation, right? We've got some shorter people with bigger feet and taller people with smaller feet. But in general, there's this upward trend. Okay? So that would be a positive linear correlation. And roughly speaking, they say if you can draw an oval around those points, that means there's at least a rough or weak linear correlation. Now that's as one variable goes up, the other goes up. We might also have a situation where as X goes up, Y goes down. For example, if you looked at the weight of various vehicles versus its gas mileage, miles per gallon. Again, there's some variation. There's some light sports cars with souped up engines that don't get very good gas mileage, but in general, your smaller vehicles actually are going to be up here, right? They're going to get a lot of miles per gallon if they're smaller and lighter. And then the heavier vehicles like big trucks and Humvees tend to get less miles per gallon. So that would be a downward trend or a negative linear correlation. Situations where there's no correlation would be if the points are just all over the place. You can't draw an oval around them, right? The best you could do would be a circle. So that would be none. Or maybe you have a situation where it goes up, there's sort of an upward trend, but then it turns around and comes back down, right? That's more of maybe a quadratic relationship, so we'll just say not linear. So we're not going to look at anything fancier than lines. So we'll generate the scatter plot and look at the points. You could probably do by hand as well. It's just a matter of scaling your axes, but the calculator does a good job of that. So you plot the points, you look at it. If it looks like there's a linear correlation, then the next question is, let's say if so, how strong is it? So how strong is it? So then we want to calculate something. We're going to have our calculators calculate a measure that's called the correlation coefficient, which is denoted by the letter R. this is where your calculators are really nice, because if you look in your book, in section 10.2, where it shows the formula, it's crazy. Page 513. It's got some sums of x times y's and sums of x's times sums of y's and sums of x squareds and sums of y squareds and subtracted and added and square rooted and fractioned and not even speaking correctly, but it's a complicated formula. So the good news is it's built into your calculator. There is some setting you have to change on your calculator, and I'll show you that to make sure that it shows you what R is. So that's not going to be hard. We're going to calculate this correlation coefficient. There is some interpretation of this correlation coefficient that your homework is going to ask you about, and that is good to know, but on the test I'm just going to say what's R, what's the correlation coefficient. But the interpretation of R, it's kind of an FYI, is basically it's always going to be between -1 and 1. And the closer it is to 1, the closer you are to a perfect positive linear correlation, where your points are perfectly collinear on the line slanting upward. Whereas a correlation coefficient of -1, so it's always going to be in here. This would be a perfect negative correlation, where your points are perfectly collinear slanting downward. Most of the time it's not perfectly collinear, right? But the tighter they fit a line, the closer it's going to be to -1 or 1. So 0 is when you have none. No linear correlation. They're just scattered all over the place, or maybe they go up and then they go down. So if you have a correlation coefficient of like 0.1 something, 0.2 something, that's not really a linear correlation. Whereas if it's positive or negative 0.7 or positive or negative 0.8, 0.9, then you do have a linear correlation. And there's a cutoff for what's considered statistically significant, given in a table. It's table A6 on page 740. In your homework, they're going to give you a link to it, so you can just pull it up. And what you do is you look at sample size, how many pairs of points you have, how many points, and then a level of significance that they call alpha, the Greek letter alpha. It's either 0.05 or 0.01. And we'll talk about more of this level of significance later, so this is kind of a preview of what we're going to be doing in the last section, the last unit of this course. In the last unit of this course, we're going to be doing chapters 7, 8, and 9. This is chapter 10, right? So they think we've done this already. So I'm just going to give you a little glimpse of statistical significance, and we'll focus on more of it later. But they're going to say, is this a statistically significant correlation? And so you're going to have to look up in the table, and they're going to tell you what level to use. 5%, 0.05 is like a 5% chance of being wrong, loosely speaking. That's what we call statistically significant. You're pretty sure you're right. You're pretty sure there is. You're 95% sure. Whereas a 0.01 level is a 1% chance of being wrong. That's a highly statistically significant. So if you look at this table, you'll see, maybe for a small sample size of 10, where it shows cutoffs. These are called critical values. Page 740. Let's see, when n is 10, 0.632 and 0.765. So basically, if we're beyond either positive 0.632 or negative 0.632, those would be the critical values for being a statistically significant correlation. So if it's closer to 1 or -1 than those numbers, then that's significant at the 5% level. right? And if it's beyond 0.765 or negative 0.765, then it's highly statistically significant. All right, so that's kind of the interpretation of R. So it measures how tightly those points are around the line, and then there's these cutoffs for what is considered statistically significant. Okay. The main thing is to be able to calculate that value. All right, so that's all section 10.2. Then section 10.3 says, all right, you got some data, some points. You've decided maybe you've got a correlation, a strong correlation. Well, in that case, then what is the linear relationship? What is the equation of the line that fits those data the best? Well, do you remember the equation of a line?
Y equals mx plus b.
You got it. So the next thing is, what is the linear relationship? In other words, the mathematical equation of the line that relates x and y. This is called the
slope-intercept one. Well, no.
That is, but here in this situation, it's called the regression line. And you're right, it's y equal mx plus b. And the two determining characteristics of any line are the slope and the y-intercept.
Sometimes the slope can be represented as a fraction too. Like,
yeah, we're going to get these numbers as decimals.
Oh, okay.
Yeah. Now, y'all know that that's the same thing as saying y equals b plus mx, right? Your book is going to do it this way. It's going to put the y-intercept first and then the slope times x. It's also going to use different letters. It's going to use b sub 0 for the y-intercept and b1 for the slope. That's in the text and in the homework. And the ampersand homework. Now on your calculator, it does it this way. But it uses A for the slope. So this is A on the calculator. And this is still B on the calculator. So it does y equal ax plus b. But the main thing is that it's going to give you the slope and the y-intercept. You just have to put the slope next to x and the y-intercept added on and set it equal to y, and you got the equation. Okay, so I'm going to show you. Just giving you the broad overview. And then the last thing we're going to do is use the equation. And this is under certain conditions. To predict or calculate y for a given x. So, for example, someone wears a size 8 shoe, how tall would you expect that person to be? We've got this data on shoe size versus height, and we've got a line that models that. That's what we call it. When we find the best fit line, it models that data. So then you can say, all right, well, where, would 8, what point would correspond to the height? What would the height be for a shoe size of 8? Now, the certain conditions. It has to be a significant linear correlation. If it's not a significant linear correlation, then the equation is useless. So that'll be a given for the test and for the homework. For the test. Let me go back over here. Oh good, I have some more space. I will have all of chapter 10 on the board. And then I'm going to try that computer again. See if I can pull up the calculator to show you.
You're welcome to use my emulator to show them if you want.
Yeah, I don't know if I can project that. That's an idea. All right, thank you. So, the conditions, when to use the regression equation. would be on a test when you're told to. Ha ha ha. Okay, if I say use the regression equation to calculate y for a given x, we do it. Alright.
So the regression equation is the y equals mx?
Right, with the numbers put in, yep. Alright, so the other situations is when the correlation is statistically significant. On the test, that's going to be the case, but in the homework, they're going to bring up this table. They're going to say, is this significant? And if it's not, then to calculate a y, you just average all of the y's. So if it's not, I'm just going to say use the average of the y's for the best predictor or estimate.
Excuse me.
Basically, if we don't know there's a relationship, then we don't know it, and then x doesn't really tell us anything about y. So to predict a value of y, just take the average of the y's. That's the best you can do to predict a y. It's just average the known y's. So what we're going to be doing is we're going to be putting the x's in list 1 and the y's in list 2. So to average the y's, you can do your one variable stats and just tell it to use list 2. And then x bar will actually be the average of the y's. So I'll show you that. The third thing is the given x value has to be, say is, in the interval of known x's. Otherwise, you just say can't do it. Actually, that it's not meaningful. So they might say, if meaningful, calculate y for a given x. Well, if the x that they give you is somewhere in between the known x's, then your line applies and you can calculate y. They actually call that y hat for calculating y. Whereas if your x is way out here, we don't know if that relationship continues past the known points. So that would be what we call extrapolating. So here it's like, we don't know. We don't know what y would go with an x way out there. Okay, so that's what they say. If it's meaningful, calculate y for a given x. If the x is outside the interval, then we can't do it. All right, soak that up into your brains while I try to get this going again.
Okay, I have a genuine question. Like, you see how when you graph it, it looks like they're all scattered? Why is that? I mean, they're together, but it looks like a scatter plot. You see what I'm saying?
When you have data, a bunch of different people or something like that, it's typically pretty spread out. And the question really that we're looking at is, is it scattered in a kind of a linear form? Is there an upward or downward trend to those scatters?
I just had never seen a scatter plot like this. It's always been like way scattered. You get what I'm saying? It's always been more scattered than.
It depends on the data. I'm trying to restart here. Fingers.
I know there was sound involved this morning. There was sound involved this morning.
Really? So it's like, my stat lab is working, but my computer system at tech is not working. So yeah, it's not one thing, it's not working. Yeah, let's go ahead and take a break. Good night. And I might see if I can hook your computer up
All right.
to this.
All right. Well, you'll have to give me a calculator because I ain't got one.